Okay, yeah, we were talking just before the break about the viscosity of fluids and gases, and yeah, we just wanted to look at the temperature and pressure sensitivity or dependence of these liquids and gases, and I just put up here the question in the as a poll. So what do you think? How does the temperature dependence look like? And the options are: it goes up with temperature for both liquids and gases, or goes down with temperature for both liquids and gases, or the viscosity goes up for gases and goes down for liquids. And I see now that well, we have a few answers, and everybody says that the viscosity would go. Oops. Let me move this thing here. How do I make this disappear? Okay, don't know. Oh, okay. So what you're saying essentially is that we have for gases it would look like this, and for gases and for liquids it would look like this. And it turns out that that your answer was all correct, of course. So now, of course, it just remains to kind of discuss a little bit why this is the case. And well, essentially for if you think of gases here, it kind of happens that, or if the temperature goes up, essentially you would have much more fluctuations or motions of the various molecules with respective to each other. And of course, that means that essentially the internal friction that you get from this larger motion would then lead to an increased viscosity. So in a way, if you have we have gases where you have all the molecules anyway flying around, higher temperature would kind of increase the internal friction. Increase internal friction as the cause for this increase. However, with fluids, with liquids, it's a little bit different because they are already kind of in a certain the atoms or the molecules are already in a certain relation with each other, and essentially it just makes it or the increased temperature essentially makes it such that that to overcome the attractive forces that you have inside the fluid is more attractive forces more easily for higher temperatures. So I guess the important thing here really is to realize that gases and liquids, they actually behave differently when it comes to a change of temperature. At the same time, typically we also assume that the viscosity is, well, I was about to say that it's insensitive to temperature. That's of course not true, but you would essentially you have a number of formulas which you then can use, in particular for air, Sutherland's law, which you can use to determine that. The other question here is, what about the pressure difference? And actually, for the pressure, it is typically like that for a pressure you would typically have an increase with an increase of the viscosity with the pressure. And that is mainly the case for gases. Again, talking about the internal friction, if you start to pressurize a certain fluid. For liquids, on the other hand, the pressure sensitivity is quite low. So the liquids are quite insensitive to pressure changes, and of course that is again related to the fact that you actually have a certain molecular structure in a liquid. But for gases, this is quite important. However, you need to realize that for ideal gases, there will be only a temperature, not a pressure sensitivity. So the temperature is actually the relevant bit to keep in mind. Okay. So much about viscosity and its measurements and some of the properties. Now the next topic would be to look at a little bit more interesting flow cases, or not, maybe not more interesting, but an additional flow case to the Couette flow case that we have looked at. So that means, if you remember very much in the beginning, we actually wrote down chapter 1 would be Couette flow. Now chapter 2 or part 2 would be Poiseuille flow. What is Poiseuille flow, and how does it differ from Couette flow? Well, we again consider that we have two walls, something like that. In Couette flow, these two walls are moving. In Poiseuille flow, these two walls are at rest, but if we have a pressure probe here and a pressure probe here, so we have P1 here and P2 here. Now the idea is that you would actually have a difference between pressure 1 and pressure 2 in this configuration. So the idea would be that pressure 1 is higher than pressure 2, so we can write that P1 is larger than P2. So you kind of press fluid through this channel. So you act as a pump, essentially. And that means that you would then get a certain velocity profile, maybe something like that, that will kind of move the fluid inside this domain. Of course, we know from the no slip boundary condition, because now we have two walls that are at rest, the velocities here need to be 0. And if you want to move, if you want to have some mass flow in this domain, you of course need to have some velocities that are non-zero. And now what we try to do is to actually calculate this velocity profile. And for that, of course, we need to again introduce a coordinate system. We have an x, y coordinate system. We do it as in Couette. We do the origin of the system, or we put that into the middle of the channel. So that means that the height of the total channel can be said that this is 2. Right, do I use B or H? I use B. Okay, then we say that the height here of the channel is 2 times B. So this here, this flow configuration, we would call Poiseuille flow, or at times we also call it plain Poiseuille flow. We will see in a second why. Or at times this is also called channel flow. So this here would be a channel. A channel is the flow between two parallel walls where you have a pressure difference driving it. Of course, there's maybe also the more familiar way of how you would look at this, namely if you would consider this to be a round pipe, something like this, where again at some cross section here, you would assume that you would have a velocity field that maybe looks like this. Maybe a little bit difficult to draw that, but I guess the idea is clear. You would have one cross section in the pipe where you have a certain velocity field. It's kind of the same idea. You have different pressures, a higher pressure in the front, lower pressure at the back, and then you press the flow through this domain. And of course, the geometrical parameter here would be the radius of this pipe. And of course, also this one here has a name. It sometimes is called Hagen. This is Hagen-Poiseuille flow. Flow. Sometimes it's called circular Poiseuille flow, or just simply pipe flow. So you see here the difference between a channel, which essentially is a kind of a two-dimensional cut through a pipe, but not axisymmetric, And then you have pipe flow, which is the axisymmetric version of a pipe. And of course, these were kind of standard geometries that people were looking at for a number of years. And historically, the two names that are associated with pipe flow is, of course, Jean Poisoy, who lived in 1797 until 1869. And he was mainly concerned about blood flow. So he wanted to know how blood is flowing, and therefore it was naturally so that he looked at these round geometries. On the German side, there was a person that was called Gotthilf Hagen, and he lived also kind of at the same time, 1797 to 1884, and he was mainly interested in engineering. So he was a civil engineer, and he looked at sewage pipes and civil engineering. I want to do right here. So civil engineering. So these two people kind of came from two different sides, but ended up with the same problem. Now, it's also interesting with all these ideas, they always came kind of at the same time for all researchers. So Jean Poisoy, he did the first measurements in like 1838, and then the theory came 1840. And Gotthilf Hagen, he was kind of looking at this in 1839, largely independent of each other. But therefore, I think the correct denomination should actually be Hagen-Poisoy flow, because it was really those two that looked at it. But for us now, at this part in the course, when we maybe cannot deal with axisymmetric flows yet, we just look at the planar version. So we look at the plane Poiseuille flow, so the thing on the left. So I guess the first question now would be, how could we possibly realize such a flow? So how could we kind of build an experiment on doing that? How would we realize that? Well, I guess a very easy way actually would be to build something like this. So you have some sort of reservoir, and then at the bottom of the reservoir we have a pipe somehow, something like that. And we have an end somewhere, and we fill this with water or with some fluid, and then of course what happens is that this fluid will go through this apparatus and then kind of come out here on the front. So that means that we have here some sort of reservoir. We have here a pipe when the flow goes through, and we have and the driving force would kind of be the pressure difference between these 2 points. So this could be P1 and this could be P2. So this could be now an experimental setup of that. If you want to actually know a little bit more about it, we can even introduce some pressures. So we can say that we have an atmospheric pressure P infinity. Here on top, we also have P infinity on this surface here. We have a height, which we can say is, I don't know, delta H, for instance. And with this, we can then calculate what is this pressure difference that we have from through the pipe. That would be something, I mean, the difference between P1 and P2, essentially. That would be the hydrostatic pressure that you have, delta H times rho times G. So that's the hydrostatic pressure of the height of this fluid column that we have in the reservoir. And now the idea is that it is exactly this, that the flow pipe flow here is driven by the pressure difference. Difference delta P. So that is what makes the flow move here. Now, of course, if we look a little bit at in more detail at these velocity profiles that we would expect here, we probably start with kind of a development length. You have some boundary layers growing from both sides, and then you would have here a region here, which is then fully developed Poisson flow. So this would be the kind of an inflow length, and then here we have Poisson flow in some way. Okay, so now let's try to actually calculate the velocity profile. So we do it exactly in the same way as we have done before for Couette flow. We start with listing a number of assumptions that we want to use. Then we take the equations, we solve them, and then we see what we get as a result. So the assumptions essentially are the same as we had for Couette. Let's start with saying, most probably, this is again a steady case, which of course is true. So the time derivative can probably be neglected. In the region where the flow is fully developed, so that means in this sketch, this region, not in the inflow region where the flow is still adapting, but in the statistically stationary and homogeneous part, we would assume that the flow is parallel and fully developed. So that means there we have ddx being 0. Keep in mind again that fully developed means the ddx of the velocity, not necessarily of the pressure. We will talk about that in a second. Then we have that the flow is two-dimensional, which means that W is 0 and ddz is 0. And then we also, of course, need to have some boundary conditions. And in this case, the boundary conditions would be that the velocity vector at the two walls, so in that sense, in that case, we say that when y is plus minus b, so if we go to our sketch, that would be when, at this point and at this point, so that the velocity at these two positions would be 0. And that's different than in Couette, because there we had a moving wall. Here, everything is 0. And that is actually a combination of the no-slip boundary condition, which is stating that the velocity in the horizontal plane is 0. So that means in the direction of the wall, or parallel to the wall. And it includes also no penetration condition, which is the velocity in the vertical direction. Okay, now having stated these assumptions, we go to the equations. So we start with the continuity equation. Continuity equation is, as you know, du dx plus dv dy plus dw dz is 0. And now we need to apply all the conditions that we have. Well, dw dz is 0, du dx is 0 because of two-dimensionality and fully developedness. What remains is, as in the case of Couette, dv dy is 0. This is something that we can integrate once in space, and then together with the boundary condition, which is no slip, with the boundary condition, we then get that v is 0. As before, as in Couette. So that's already the first result that we have. Okay. Now we need to go to the momentum equations. Also there we start with the y momentum equation. That's what I would always recommend to do. So the wall normal momentum equation first, because in this case, it's actually very straightforward and I'm not going to write it down. It will look exactly in the same way as we had for Couette, meaning that the result will be as before. And when I mentioned before as for Couette, maybe that's better. As for Couette, we get as a result dp dy is 0, which means that p is a function of x only. And of course, that's already an interesting result because it means that even though we may have a velocity profile that looks like this, it still says that the pressure is not dependent on the vertical distance, only on the streamwise distance. But here we know clearly from just this example, we know that the pressure at P1 is not the same as the pressure at P2. So there is actually a variation of the pressure as a function of x, of the streamwise distance. Okay, but I guess we now need to go on and look at the x momentum equation. And also here, as for Couette, what we get as a result is that we have 1 over rho of dp dx is nu times d squared u dy squared. Actually, I can also change these derivative signs here to be ordinary derivatives. These are not partial derivatives anymore because I know that the pressure is only a function of x and not of y anymore. So there's no partial derivative there anymore. Okay, well, this here means that I can just identify now or isolate the velocity on one side. So we have du squared dy squared is simply 1 divided by mu dp dx. So now I just need to integrate, I would need to integrate this equation. Before we do that, I again would like to just notice a few observations here. Well, first of all, as in the case for Couette, we again have essentially eliminated all the acceleration terms. The left-hand side of the Navier-Stokes equations, all the terms were 0. The only thing that was left was a balance between the viscous forces, which are essentially these. Oh, we can even just write it, I guess. So we have the viscous forces, and on the left-hand side here we have the pressure forces, or the pressure gradient, maybe. So what the x momentum equation in the end does, it just says that there's a balance between the viscous forces and the pressure gradient. All the acceleration is gone. So no acceleration. That means the left-hand side of Navier-Stokes was all 0. And what is left is a balance between the viscous forces and pressure gradient. So that's kind of the physical interpretation of what is left. Okay, but now we can integrate this equation twice in the vertical direction in y. It's quite easy to do because we know that dp dx is not a function of y, so we just integrate it, so it's not a partial derivative anymore. So that means we integrate and we get u to be 1 over 2 mu times dp dx. And this is times y squared. And then we have two integration constants, a times y plus b. And the boundary conditions we have mentioned above. The boundary conditions for here, where is it? Up here. The boundary conditions, because now we're only talking about u, the boundary conditions would be u at plus minus b is 0. So that means with the boundary conditions which state that u at plus minus b is 0, we can find very easily the following result, that a needs to be 0 and b will be minus 1 divided by 2 mu dp dx times b squared. So if we now plug in everything back in the equation, we can then get our final result for Poisson flow, which reads simply u is minus b squared divided by 2 nu times dp dx, and then we get 1 minus y divided by b squared. So this here is the velocity profile of Poisson flow. It is a little bit different now than the one that we got for Couette flow. Well, maybe first, just for completeness, v and w were actually 0. That's really, should just add that here. So this is now the complete velocity profile. This is a little bit different than for Couette, and it's different because we actually didn't have a 0 here, but we rather had a pressure gradient. So that means that the integration actually gave a squared term. So the shape of this, because we have this square here, the shape of this is actually the one of a parabola. So if I'm now trying to sketch this, if this is u and this is y, then we have plus minus b. So this is minus b, this is plus b. So the velocity profile perhaps looks like this. So something like this. And this is a very kind of a typical, typical result that you will kind of hear always. For a channel flow, for a pipe flow, you will have a parabolic velocity profile. This is simply the result of the Navier-Stokes equations. Now we actually see kind of an interesting thing which you can use to rewrite or simplify maybe the profile a little bit. You realize that of course there's a maximum somewhere of this profile, and that is here in the middle at y being 0. And this particular velocity here is called UCL for the center line velocity. So that's the velocity in the center. And of course, now from the equation, you can directly see what this UCL is. Well, it's essentially this factor here. This one here would be UCL, because you realize if you put y to be 0 in the equation, then you just get a factor of 1 here in the brackets. So this UCL is minus b squared divided by 2 mu times dp dx. This is the center line velocity. A quick question here. I didn't prepare a poll for that, but maybe one of you can answer. Why is this negative? Why is there a minus sign? Minus b squared divided by 2 mu times dp dx. I mean, the velocity is positive. Why is there a negative sign?
Because the pressure gradient is negative.
Exactly. Exactly. It's important to realize that this one here is actually negative. Exactly. That's important to keep in mind that, again, if you just look here, for instance, in this example, P1 is larger than P2. So that means the pressure actually goes down along the pipe, meaning dP dx is negative. So therefore, this actually becomes positive in the end. But this is actually something important also to keep in mind. If you have a pipe, if you have a channel, the pressure decreases along you go downstream. We will talk about that later as well, why this is the case. But for now, this is just important to realize there is a negative pressure gradient in a pipe. So let me just write that down. To drive the flow, in this case, the pipe or in the channel flow, to drive the flow in the positive x direction, well, what we need to do, we need to apply a negative pressure gradient. So that means that this dP dx is actually lower than 0. Okay, so that was one thing, this UCL. There is actually a second velocity that we sometimes use. And I would also like to introduce that right now to characterize this flow. And that is actually related to the flow rate in this configuration, which you then can also express as a velocity, which I will tell you in a minute. But the flow rate in this channel configuration, which we can say is Q for a volume or mass flow, well, that would essentially just be the integral of from minus b to plus b of the velocity as a function of y times dy. And now you can, of course, if you want, I'm not going to do that here, but I just want to mention, of course, you could have here also kind of the span-wise extent. So if you would now consider maybe here, if you would consider kind of a third dimension, which has a thickness d, you could add this here in the flow rate. So actually, perhaps what we can do to simplify it here, we can write like this. This is Q divided by D. So that's the flow rate per width. Okay. So we can define this as being the integral between minus b and b of the velocity profile, and this we can now use as a definition. That's why I'm doing here 3 lines to say that this is actually a definition. We can say that this is another velocity, which we call ub times the height of the channel which is 2b. Now, what is this ub? Well, this ub would now be, taking maybe a red here, this would be the velocity if we assumed that everything was uniform that everything was a constant. So this here would be ub. So we assume that we have the velocity everywhere the same, but it has the same flow rate as the pink or the turquoise. No, that's not turquoise. Pink, purple as the purple. And this is called this is called the so-called bulk velocity. So we have now defined 2 different velocities: the centerline velocity, which is the one in the middle, and the bulk velocity, which corresponds to kind of the average velocity in some way. Yeah. So the bulk, the UB is the bulk velocity, or the average velocity. And of course, now we can actually calculate it for this example of plane Poisson flow. Well, maybe first I can just write the definition. So UB, if I'm just isolating this, would be 1 divided by 2b of Q, or would Q over D again, which would be the same as 1 divided by 2b of the integral from minus b to plus b of u of y times dy. Now for plane Poisson flow, we can actually calculate all of these quantities. And now let's do that, just to do that for plane Poisson flow. Well, UB, if we start there, UB would be just using this formula that we just derived. It's the integral from minus b to plus b of, well, let's do like this, UCL of 1 minus y divided by b squared dy. Now I can just do these integrations. Well, that gives me, and just do that a little bit step by step. It's UCL divided by 2b, that's a constant. And then I just integrate these two terms. It's y minus y to the 3 divided by b squared. And this gives me then, this I need to evaluate between minus b and plus b. And if I do that, I will get as a result 2/3 of UCL. So that means, and that's I guess an interesting and relevant result, UB is 2/3 of UCL. This is something that is valid for plane Poisson flow. So that means if I'm going now to my little sketch that I had up here, which I hope I did it kind of correctly, UCL here, if this is 1, then this should be at 2/3. So the bulk velocity in a channel is 2/3 of the centerline velocity. So if somebody tells you, well, I have a channel flow with U bulk of 1 meter per second, I can directly tell you, okay, the centerline velocity would be 1.33. 1.5, sorry, 1.5 meters per second. Okay, so this is the bulk velocity as a function of centerline velocity. But we can also calculate all the other things that we did for Couette. So for instance, we could calculate now based on this profile, the wall shear stress. And the wall shear stress, tau wall, well, we know the definition. Mu times du dy at the wall. And now because we know what the profile is, we can just evaluate that. And now it becomes 2 mu times UCL divided by B. This is the result for the wall shear stress. I mean, you can do all these calculations at home afterwards if you want. So we don't need to do all these derivations here now. But this is the wall shear stress. I can do the skin friction coefficient. So CF. CF, as we said before, that's just the wall shear stress normalized with the dynamic pressure. So tau wall divided by 1/2 rho U squared, and here I can take UCL for the channel as the quantity to normalize with, and that would give me then 4 divided by Reynolds. And the Reynolds number in this case could be defined or is defined as UCL times B divided by nu. And that is actually what we call a centerline velocity, centerline Reynolds number. So in this case, as I was saying, the Reynolds number is based on the centerline velocity, based on the center line velocity. And the what we call the channel half height, P. So the center line velocity, that's UCL, and the channel half height, P. Okay. So, so this is now, these are all the quantities that you need to know for Poiseuille flow or plane Poiseuille flow. We have calculated now the profile, which is given here, the parabola. Again, keep in mind that's always a parabola for this type of flow, where the negative pressure gradient goes in. We have defined the centerline velocity. We've then defined the bulk velocity, which is the relation is given here as 2/3. Then we have calculated the wall shear stress and the skin friction coefficient as CF being 4 divided by Reynolds. Keep in mind, for Couette, it was 2 divided by Reynolds. It doesn't really matter so much what this factor is. The important thing is that, again, it is linear in the speed or in the pressure gradient. And that, I guess, is the important realization. Okay. Now,
Professor.
Yeah.
I have a question. Inside the integral of UB, shouldn't there be a free at the denominator after performing the integral?
Actually, I was also thinking that something is a bit weird there. Let's do it properly. Let's see. Okay, so we integrate that. So UC and 2B. Okay, 1. This is Y. This is this. There needs to be 1/3. Huh? This you mean, huh?
Yes, I meant this.
Yeah, no, exactly. I think that also becomes correct now. Yeah, because what you have now, you have you evaluated. So let's do that properly. So you have UCL divided by 2B of B minus let's run B to the 3 divided by 3B squared, right? Then you have minus B, and this one becomes minus plus. No, minus again. No, wait. Oh, this is a plus, of course. Plus B, and it's the same thing, huh? Like this. So, so that all goes. This goes away with this one. So we have this one goes away. So yeah, of course that's now 1/3, 2/3. Yeah, 2/3. Okay. Yes. Now it's correct. Okay. So this is all good. Now I was actually wondering when I was writing down. It was wrong in my notes, but now it's correct. Okay, sorry about that. Okay, very good. But then I think we can directly take a break now for another 15 minutes, and at 5:15 we continue. And I would say one last thing about channels and pipes, so plane and circular Poiseuille flow. But then we move on to start to talk about the vorticity equations, which is also a very interesting topic. Okay, but let's take a break for now, and we continue after the break.